So, good morning, dear students. So, in this class, let me discuss a theorem based on convergent sequence. So, what is the meaning of convergent sequence? A sequence an is said to converge to L if for each epsilon greater than 0 there exists a positive integer m such that modulus of an minus L is less than epsilon for all n greater than or equal to m. So, we are using that definition to prove our theorem. So, what is the theorem statement? The theorem statement says every convergent sequence is bounded. So, we have to use here convergent sequence definition, and if we have to prove how to use convergent sequence definition and to prove how to prove it is bounded. Okay, so here we are using the definition of convergent sequence. The proof for this is, let n be a convergent sequence and it is converging to L, for epsilon greater than 0, there exists a positive integer m such that modulus of n minus L is less than epsilon for all n greater than or equal to m. So, while defining limit of a sequence, we have came across this term. Okay, means a sequence, let n be a sequence and L belongs to R. L is said to be limit point of a sequence an if for each epsilon greater than 0 there exists a positive integer m such that modulus of n minus L is less than epsilon. After that, I have given there a note, that is this sequence means this term can be expressed in the form of this. Okay, so here I am using that term only, that note only. So here modulus of n minus L is less than epsilon. So here we can write this in the form of this. So L minus epsilon, n is less than L plus epsilon, because a sequence this is converging to L means it has lower bound as well as upper bound. Okay, lower bound as well as upper bound means this is of the form modulus of n minus L is less than. So here I am writing the bounds for this. So L minus epsilon is less than, n is less than L plus epsilon for all n greater than equal to m. So here I am writing let k1 is equal to minimum of a1 a2 am minus 1 comma L minus epsilon. Okay, and k2 is equal to maximum of a1 a2 am minus 1 L plus epsilon. So here in the sequence I am denoting minimum terms as well as maximum terms. Okay, so then I can express that then k1 is less than or equal to n is less than or equal to k2 for all n belongs to n. So here we have got lower bound as well as upper bound, then we can say this sequence is bounded sequence. So to prove every convergent sequence is bounded, here what we have taken, first we have taken the definition of convergent sequence. After we have modified that in the form of this. So here we have taken minimum of a1 a2 m minus 1 L minus epsilon as k1 and maximum of a1 a2 am minus 1 L plus epsilon as k2. Okay, so therefore this can be written as k1 is less than or equal to k2 is an is less than or equal to k2 for all n belongs to n. So here we have got lower bound as well as upper bound, then this sequence is bounded sequence. So previously in the question papers they have asked that every convergent sequence is bounded. Is the converse part is true? Justify. So for that I have written here note, the converse of the above theorem is not true, because every bounded sequence is not a convergent sequence. Okay, so that is a bounded sequence is not necessarily a convergent sequence. For example, consider the sequence an defined by an is equal to minus 1 to the power n. Clearly this sequence is bounded. Because the range of the sequence this is, if n is odd we get minus 1, and if n is even we get plus 1. So because this sequence range is minus 1 and 1. So therefore minus 1 is the greatest lower bound of the sequence an and 1 is the least upper bound of the sequence an. So here there are two bounds, that is minus 1 and 1. But a sequence is said to means a sequence is convergent if and only if it has a unique limit, not more than one limit. Here we are getting two limits. Therefore here but it is not a convergent sequence. Which one is? An is equal to minus 1 to the power n. Okay, so next is monotonic sequence. Monotonic sequence. A sequence n is said to be monotonically increasing. A sequence n is said to be monotonically increasing if n plus 1 is greater than or equal to an for all n belongs to n. So that implies that a1 is less than or equal to a2 is less than or equal to an is less than or equal to n plus 1 and so on. So this can be expressed in the form of so n. So if I subtract an both sides, so then it will become an plus 1 minus an is strictly greater than equal to 0. Okay, so then also that sequence is called as monotonically increasing sequence. Okay, so next, a sequence n is said to be monotonically decreasing sequence if n plus 1 is less than or equal to an for all n belongs to n. So here a1 is greater than or equal to a2 is greater than or equal to an is greater than or equal to an plus 1, or this can be expressed in terms of an plus 1 minus an is less than or equal to 0. Less than or equal to 0. A sequence n is said to be monotonic if it is either monotonically increasing or monotonically decreasing. A sequence n is said to be monotonic if it is either monotonically increasing or monotonically decreasing. So next concept is a sequence an is said to be strictly monotonic increasing sequence if n plus 1 is greater than an for all n belongs to n. So this can be expressed as an plus 1. If we subtract an both sides, then it is like this. So then also that sequence is called as strictly monotonically increasing sequence. A sequence an is said to be strictly monotonically decreasing sequence if n plus 1 is less than an for all n belongs to n, and this can be expressed as if we subtract n both sides, then it will be like this, that is n plus 1 minus an is less than 0. Next is a sequence n is said to be strictly monotonic if it is either strictly monotonically increasing or strictly monotonically decreasing. A sequence n is said to be strictly monotonic if it is either strictly monotonically increasing or strictly monotonically decreasing. So these are all some examples based on about definitions. First one is sequence 1, 2, 3, n. So what we are getting here? So 1. So bigger than 1, 2, bigger than 2, 3, bigger than 3, so on, like that. So here increasing, that is not, terms are not repeating here, but this is in the order, increasing order. So here is strictly monotonically increasing sequence. So 2, 4, 6, 8, like that, even numbers. So that is also in the form of strictly monotonically increasing sequence. So here 2, 2, 4, 4, 6, 6 is a monotonically increasing sequence because here n plus 1 is less than or equal to an. So here terms are repeating 2, 2, 2, 4, 4, 6, 6. Okay. So here minus 1 divided by n is strictly increasing. This is also increasing because a minus term is there. So if you put n value, then you get increasing values. Okay. 0, 1, 0, 1, like that. So what is happening here? We couldn't say. That is 0, 1, 0, 1, 0, 1, like that continuously. It is not monotonic because here we can't say it is whether it is increasing or decreasing. So next 1, 1, 1 by 3, 1 by 3, 1 by 5, 1 by 5 is a monotonically decreasing. So here value of your 1, 1, 1, 1 by 3. So next also decreasing, next also decreasing. So means here the value of the sequence is decreasing. So minus 2, 2, minus 4, 4, minus next minus 2, 2, like that. So here what is happening, we don't know whether it is increasing or decreasing. So therefore it is not monotonic. So with this I conclude this class. Thank you.